All right. Okay, so I hope everybody's doing well. Right now, last week I said that we'd probably have a test on Thursday, and that's what I put on the calendar. Today's only Monday. I will give you something that looks like this tomorrow. Not tomorrow, we'll see you tomorrow, Wednesday. We'll finish up the candle. We'll do it all day today, and probably about 10 minutes of Wednesday. And then the rest of the time, what we'll do is we'll spend time reviewing. Okay, so this is like a little review guide for chapter 1. Everybody get that? So you'll get that on that day. Another thing I want to ask you about to do is on, there are a lot of questions on this article that we're doing. And it has to do with how a candle works. What's the science of a candle? If Faraday said this, did you actually see that much science? And chances are no. Chances are, you just started out kind of in science in a way. But if you knew science well, you would see how much science there really was. So that's my job, is to try to point out some of the science that was there. You saw something, you just didn't know how to say it scientifically, okay? So that's what we're going to be doing today. So if you go ahead and get this article out, we're going to continue where we were. And so we're going to start telling a story about how a candle works. Excuse me. So at this point, I don't know if you're making a list or anything like that, but I tried to make a list of some of the words that we've already used. And then the question is, could you use these in a paragraph? That's one thing I'd like to kind of ask you to be able to do. Before you take the test on Thursday, can you write a paragraph on how a candle works and use all of these words? Now, I'm going to keep adding that list today. I'm going to add some more, a little bit more on Wednesday. But can you tell the story? So let's see if we can start all over again, okay? What does paraffin have to do with this? Does paraffin have something to do with the candle? What is paraffin? It's a wax, okay? And the wax is, if you look it up, it has a formula of C25H52. Is that correct? Now, what does that mean? If you're a compound and you're a carbon compound, what word up there means I'm a carbon compound? I'm a carbon compound. This right here, organic. So candle is organic. And by the way, the word organic was around long before the people started buying organic groceries, okay? I don't understand, when you go to the grocery store, is it organically grown? That means you pay more money. What they're talking about is that they don't use other chemicals to treat the crops and things. That's what they mean there. But the word organic in chemistry has been around since the 1800s. You get that? So organic in chemistry has been there before. All right, now, so paraffin is an organic compound, it's a carbon compound, but notice that it only contains carbon and hydrogen. What's another word for an organic compound that only contains carbon and hydrogen? Hydrocarbon. See, do you understand how I'm putting these words together? Okay, so paraffin is a wax. Paraffin is an organic compound whose formula is C25H52. Paraffin only contains carbon and hydrogen, so it's also known as a hydrocarbon. Every hydrocarbon I know of can be burned. It's a fuel. Get that? Every hydrocarbon I know of is insoluble in water. What does that mean? What does it mean if it's insoluble? I keep looking at your faces. I don't just kind of go like this. I'll know to call on you. What if I told you that salt and sugar were soluble in water? What does it mean to be insoluble? It doesn't mix at all. Right. And so it does not dissolve. You cannot dissolve wax in water, can you? That's going to play a role later on. Gasoline is probably the most famous hydrocarbon you know of. Gasoline will not mix with water. I don't care what you do. Shake it together, put it down on a jar, they will not mix. Vegetable oil will be the next one. Vegetable oil would not mix with water, will it? Okay, so anyway, we find out that there's another chemical that if you're going to make your own candles, you might want to add to it, and it's called stearin. And what did they say stearin was good for? What did stearin do? Say it again? Right, so it raised the melting point. It raised the melting point of the wax. What is the melting point? What is the melting point? I keep looking at your faces. Yes. 2 answers in a row. What is it?
It's like the degree the solid starts to melt.
What does that mean, melt?
Like, it's the temperature where it changes into a liquid.
From what?
A solid.
Right. So the melting point is the temperature at which you change from a solid to a liquid. Is that correct? Now, if stearin raises the melting point, that means it's got to get hotter and hotter before it'll start to melt, and that makes the candle last longer, didn't it? Didn't they say that some church candles were absolutely 100% stearin? They last a really long time. I had a volleyball players. Does do you have somebody helping you, a former student? Right. Names. I knew you did. Do you have something? Do you have a former student help you at the beginning of the year?
Like it's graduating?
Yeah.
Yeah, Lauren Bus.
Yeah. They just call them Bussy. What do you call it, Bus?
Yeah.
Okay. Lauren, she might be embarrassed and she might not remember this, but Lauren Buss, I still remember she did this. How many years ago? That'd be like 6 or 7 years ago, probably. She did an extra credit experiment. She happened, her parent, her mom and her, did these projects, and they would put these on wine bottles or some other kind of bottles like that. And see how they're made? And you would light them, and they melt incredibly fast. And they dripped all over the bottles. And so you could actually use one color and then another, and you had this bottle which looked like art. It was like artwork. And so the question was, she wondered, what about these candles? So here it is. This is really good extra credit. She actually looks on the box, finds the company, emails them, all right, and wants to know, we're doing a project in chemistry, and talking about they add stearin to candles, blah, 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 blah. And he said, I was wondering about your candles. And they wrote back, said, we don't have any stearin in ours at all. We want it to melt at a lower temperature because we want it to melt so fast that it drips off and makes the artwork. And then the company sent her like 3 boxes of these for free. She gave me one. Well, anyway, I thought that was some pretty neat work. She got that from the lesson. She heard the lesson about what stearin did, and then something in her life says, but these don't. These melt quickly. And that's why she wanted to know what was going on. Oh, for most students, sorry. That's these candles right here. Okay. Anyway, that's pretty good. Now, we went down here, and let's see what else we had. Oh, okay. Then we went to the next page, down at the bottom of this page, and talked about the wick. And even though I read this article about 30 years ago, I had never heard that word before that, and it was called mordanting. What in the world is mordanting? And they put in parentheses the word pickling. And pickling is a chemical process, and we actually do it to cucumbers. And when you take cucumbers, small cucumbers, and you put them in a chemical, it will actually make them get a little crisper and firmer. And then we don't call them cucumbers anymore. What do we call them? Pickles. That's right. And that's where pickles come from. And then we put it in mostly vinegar. Pickle juice is mostly vinegar, and that's all of a sudden you got yourself a pickle. So you can actually pickle different things. Have anybody ever had pickled pig's feet? They actually sell those. You have? Wow. What's it taste like?
I thought you said heard of, not eat.
Oh, okay. All right. Has anybody had pickled eggs? Okay, so you actually can use a chemical reaction to make things a little different. So somebody figured out that, I don't know how they did this, they figured out this chemical here, when you soak the wicks in there and they get pickled, then when you put them in the candle, what happens to the candle? What happens to the flame? Or what happens to the wick, I should say? Why would somebody want to spend the extra money and time to mordant a wick? Yes.
It doesn't smoke.
Right. It makes less smoke. So it means at one time all candles must have had a lot of smoke, right? So they have less smoke, and it also don't get any ash. You don't get like the end of the wick just falling off like that. I actually come from an era where smoking was big. Everybody on TV and movies smoked, and especially teenagers thought, wow, if I want to be seen as an adult, I'll start smoking. And it was just a terrible climate. I didn't smoke. Both my parents smoked, and I smell smoke all the time. And so we had ashtrays. You don't know what these are. We had ashtrays around the house, and they had cigarettes. You'd sit the cigarette there, and you'd go do something, and it would just keep burning. And guess what would happen? It just kept burning. This real ash occurred in it, and you had to tap it, and the ash would go into the ashtray. Every car had built-in ashtrays. I use mine to put change in. But anyway, I don't know if they still make them. Do they still make ashtrays? Do they? Really? Okay. Well, anyway, so this is going to make less ash also. And then it said here, it inhibits smoking, and let's see, what else? Then we talked about you better have the right size wick for the right candle. Remember that? If you have too big of a wick, what happens? Too big of a wick for the diameter. And I haven't seen you for about 3 days, but what happens when you have too big of a wick in a candle? Anybody? Yes.
Will it smoke a lot?
It did. It smoked a lot. And you don't know why yet. You will. You will know why. And what about too small of a wick? Yes.
Small flame.
Almost no light, very weak flame, and almost doesn't keep itself going like that. Anyway, then we got into, this says here, how to make it, and we talked about a double boiler. And one thing I told you didn't know is how dangerous vaporized candle was. If you vaporize candle, you're talking about a fuel just waiting to explode, essentially. So it's very, very dangerous. Then we got down to the bottom here, and this is kind of where the story starts, okay? So we told part of the story, but look down here, and let's start the, if you told somebody, hey, you know what? I know how a candle works. And even if you wanted to tell them all that stuff, you could, but here's how the part of the story starts. Number one, you light the wick. Why? Why do I light the wick? Now, somebody hadn't answered one yet. How about that? Somebody hadn't raised their hand yet. Why do you light the wick? I know you haven't been here for 3 days. Yes?
Well, it's because you melt the wax.
Yes. The only reason I need to light that wick is I need heat to do what? To melt the wax. Is that important? Yes. And then it says here, the flame melts the wax near the wick. Then the liquid wax is pulled up by the wick by capillary attraction. And this is where we kind of left off last week, and I can redo the demonstration, I think. Let me see if I can redo it. I didn't clean this up. We had some food coloring, and if I put a capillary tube next to it, whoops, I'm not going to suck it up or anything like that. It's going to go up by itself. But what's the science behind this? And we had these two words. The capillary attraction, also known as capillarity, has to do with adhesion and cohesion. Which word would you use to describe the fact that food color and glass are attracted to each other? The attraction of glass and food coloring, what word would you use for that? And my memory trick was, if the two materials are different, then it's adhesion. If I stick tape to a table, adhesion or cohesion? That's why they call it adhesive tape. Now, after the glass attracts the liquid, then the liquid attracts itself. What do you call it when the liquid attracts the liquid and pulls some more up with it? Cohesion. You put those two together and you get a thing called capillary attraction. also known by the common name of what? What's the common name? Wicking, okay? It's called wicking. This is a little story, it's a true story. I have a house where I don't have brick on the outside. I have this kind of like boards, they're like clapboards, they call them. And even though they had a lawsuit against this company, here's what happens. The rain was supposed to, whenever you put these on, you're supposed to put the bottom on, then the next on there, and the rain's supposed to go all on the top. So that's the way you do it. Same thing with shingles. So you have to put a shingle down, put the next layer, so the rain will go off them, okay? Well, what was happening is the rain was going down the clapboards, the boards, and it got to the bottom. And then what was happening, here is the board, the last board, and here's the brick wall down at the very, very bottom. Well, there's a gap there. See? There's a little gap there. And so it would cling to that thing, and it got on the back, and it went behind it. How did it go behind it? How would the water get behind that board? And you know what they called it? Wicking. It would wick its way up the board. Well, then it would get up behind there, and it would rot out the wood behind the siding. Ah, see that? No? Okay, that's called wicking. All right. Now, you might say to yourself, well, I don't know of any capillary tubes in the wick. That's right. But what if I do this? What if I just said, I'm not going to put anything inside the capillary tube. I'm just going to put it on the outside of the capillary tube. What if I just put it on the outside? Then what happens? Isn't it still drawn up? Isn't it drawn along the side? So I don't have to be inside of a tube. I could be on the outside of a tube, right? And what if I had this fiber and this fiber, and who counted the fibers in the wick? And you told me how many? Remember that? 12 different fibers like this. And when you get a liquid on there, it's going to wick its way along those sides of those fibers all the way up like that. It's going to keep wicking its way up. All right. Now, is that important? Okay, is that important? It said here, let's turn the page now. And it says here, it's going to, you light the wick, it melts the wax. Liquid wax is drawn up the wick by capillary attraction. Everybody got that? Then what? As it climbs near the top of the wick, it is what? Vaporized. What does that mean? Yes.
State change from liquid to gas.
It changed from a liquid to a gas. And so as it climbs up the wick, it gets hotter and hotter there, and it changes to a gas. Well, wait a minute. Well, then what's burning? I thought the wick is what was burning. Oh, yeah? Try a real piece of wick that's not in a candle. Try them this big and burn it. How much heat and light do you get out of that? 5 seconds? 10 seconds? That's it. That can't be it. That candle burns for hours. It can't be the wick that's burning. I need to light the wick, but that's not what's burning. Okay, that must be the candle. Well, the flame never touches the candle. Well, then it's the liquid. That's it. It's the liquid candle. It could be, but some of you actually poured liquid candle down and tried to light, didn't you? What happened? Didn't light. What happened? So what is it that's really being lit? It's not the solid candle. It's not the liquid candle, but it gets hot enough, it turns to a what? A gas or a vapor, right? Is that correct? Now, it just so happens that when you have a hot gas on this planet and you have air, which is not as hot, it gets buoyed up. Or you can say it rises. How about that? If I put hot air balloon, what makes it go up? See that? It's the air in there is less dense, and you got this other air around that's more dense. It actually pushes it up. And so where does the hot gas is forced to go in what direction? Up. Even if you turn the candle sideways, which way does the flame go? Up. Now you might understand that. It's this hot gas that is going up. Now on the very last page here, one of the last pages of the article, I tried to draw, I got this from a book, but it didn't come out very well, so I had to draw it. The first is a regular candle flame. And over here, this is what you should have seen if the picture had come out very well. If you were to go in orbit, and they did this in the space shuttle, it also works in the International Space Station, you can do that. If you're orbiting the Earth, you're in what they call microgravity or, quote, zero gravity. It looks as if there's no gravity there. You get that? It feels as if there's no gravity. Well, if you're in a quote, zero-G environment, there really is no up. The gravity's pulling my air down, and the air tends to push the hot gas up. But what if there is no down or up? Now which way does the flame go? And in the space shuttle, the flame looks like that. It's a ball. It doesn't go up. It's not pointed upwards. And it's also blue. It's almost no yellow. It's almost all blue, and it's round. We're going to talk about that too, okay? Why does the flame go up, and why is the flame yellow? We're going to talk about that today. I will tell you one thing. I've only had one student in all my time try this, but if you had some kind of device like a turntable, something that you know could turn, records play on a turntable, all right, you could put a piece of wood on there and some little glasses and make sure they don't fall off. And then you put candles in them and make sure the candle flame is lower than the top of the glass. You don't want the air to mess around, okay? And if you just light the candles, the flames go like this. But then if you start turning them at a certain speed, does anybody know what they're going to do? Now, the flames are lower than the lip of the glass. And if you keep turning it, here's the flames will go like this. And they'll point that way. What's that all about? Well, as this thing goes around and around and around in those glasses, a lot of the air is pushed to the outside of the glass. So now you have real dense air there and less dense air here. And this air is, the vaporized fuel is going to go up. For them, up is toward the less dense gas. See that? And so the flames will actually start going inwards like that. Okay, let's go on. Let's go back to our article. Okay, now let's go to the next one. It says here, the flame has the interesting features I noticed as a child. Just above the wick, you see a dark cone that is top of the yellow region responsible for most of the light. On the sides of the flame and near the wick, there is a blue region. Depending on the diameter of the wick and the height of the flame, the blue region may only be a fraction of the height of the flame, or it may nearly reach the top of the yellow region. It is surprising that the vaporized fuel molecules, what are they? What is the vaporized fuel? Oh, I lost you. Paraffin. What is the vaporized fuel? It's candle, isn't it? Candle wax. Why, since you only have one type of fuel, why would you get three kinds of flames? The yellow flame, the dark zone, and the blue zone. Why? Why do you get that? I don't get that on the space shuttle. I only get one, blue zone. Have we talked about the different zones yet of the flame? Let's go back to page 1 again. Please don't learn this because I told you it was going to be on the test, but it is going to be on the test. But I want you to learn it because if you read this article already, you know that the author said that there were 3 zones of a candle flame, right? And the first one was the bright yellow part called the luminous zone. Everybody get that? So the yellow part is called the luminous zone. It has the most amount of light coming from it, and to illuminate means to give off light. If you're a fan of Disney, you know that in Beauty and the Beast, the candlestick had a name. What was the candlestick's name? Lumiere. Oh, that was so tricky. Okay, Lumiere. Okay. Anyway, so the luminous zone is the yellow zone, and then we had the dark zone. Guess what they called that? The dark zone. Yes. And then the blue zone had the name reaction zone, And we'll talk about that very soon, because there's a lot of different chemical reactions taking place in that blue zone. So that would be an easy question to say luminous zone, dark zone, and the reaction zone, this blue area. See that? Now let's do the temperatures, okay? What are the temperatures of the flame? And even though we had a thermocouple, and Max, you did that with the thermocouple, right? And I don't know if you got these same numbers or not, but this person actually used some very sophisticated equipment. At the wick, you're talking about 600 degrees Celsius. That's way up there. And right above the wick, 800. At the top of the dark zone, 1,000. Above the dark zone, 1,200. So you see how they're going by 200s? 600, 800, 1,000, 1,200. Get that? Now that's how you memorize those by 200, in steps of 200, right? But what's the last one you want to mark? Where's the actual hottest part of the flame? And it's none of those. Where's the hottest part? It's this blue zone. And what do you see? Near the top of the blue zone, that's 1,400 degrees. And that's where the hottest part of the flame is, right there. So anyway, when you're reading this, it talks about, right in through here, it talks about these different areas of the flame. I want to get to the science of this part right here, okay? See this paragraph right here? Okay, let's take a look at this one. In the modern classification of flames, the type of flame produced by a candle is called a diffusion flame, or diffusion-fed flame, same thing. Another familiar type is premixed flame. The commonest examples are seen in Bunsen burners and gas stove. In a diffusion flame, the rate of combustion is determined by the rate at which the gas diffuse through each other. Whereas in a premixed flame, the gases are mixed prior to burning, and the rate of combustion depends on the flow rate of the fuel, the mixed fuel. For example, stove gas is mixed with air before it reaches the burner outlets. Further classification of flames include, and we'll talk about that later. No, we won't talk about that at all, right? Okay, one more time. So let's talk about that word combustion. So here we go. So far I've used all these words. Here's a new word for you. So we use this all year. We use the word combustion all year. In chemistry, anytime you combine with oxygen, I'm going to use the word burning. Okay? If I say burning, you always say chemical reaction, because it means you're chemically reacting with oxygen. Get that? But not all burning is combustion. Burning means combine with oxygen. I can burn a piece of iron. That means I'm going to combine with oxygen. But what is combustion? Combustion means the thing you're burning is a carbon-hydrogen compound. It can have oxygen too, but it has at least carbon and hydrogen in it. So, was combustion taking place in the candle? Was the candle burning? If it was burning, it had to be undergoing combustion. Was it combustion? Was the fuel a carbon-hydrogen fuel? Yes. And where did this come from? Where? From the air. I find this, many students, even when they graduate, they still don't know what air is. You know? I'm not sure why, but somehow you get this idea that air is oxygen. I'm not sure why. 80% of it, 80% of the air, every time you take a breath, is something you don't do anything with. You don't do anything with it. It's nitrogen. Almost 80% of the breath is nitrogen. That's in your air. And about 20% is oxygen. That's what you want. So when you hear about scuba divers that, and by the way, guess what's in scuba tanks? What's in a scuba tank? It starts with an A. Air. Scuba tanks have air in them. Now, if you're a scuba diver and you have air and you go down very deep and you stay down too long, you have to come up and sit into the water and decompress. You have to give time for the nitrogen to come out of your bloodstream, because it doesn't want to come out very, very quickly, or else you can have the bends. But there are divers whose job is to stay underwater for hours. And they don't have time to decompress all the time. So they give them tanks that might have something like 80% helium, 20% oxygen. That's a different kind of air, isn't it? All they really want is the 20% oxygen, and helium is inert. It goes into your lungs, it comes out easily. And so you could keep a diver underwater and not decompress with a helium oxygen tank like that. Okay, so anyway, where's the oxygen coming from for the combustion? From the air. Now, let's go back to 9th grade. Why would oxygen, right here, why would it go toward the flame? I look at everybody's faces because, again, I'm trying to teach you science. You may not be able to put this together, but why would oxygen over here move toward the flame? I'll give you a little clue. You knew this word in 9th grade. If I opened up a little bottle of perfume right here, you would smell it first, and then you, and then you, and then you. What's it called? Diffusion. It said that a candle was a diffusion-fed flame. So let's think about what that means. The oxygen right next to the flame is going to be combined and burned and used for burning, right? But then there's no oxygen there. But right next to it is 20% oxygen. Diffusion is the movement of chemicals from what? Areas of higher concentration to lower. If you gobble up all my oxygen right here, I'm coming. But how fast do I come in? I'm bouncing around, and there's a gap. I'm getting there, and I'll bounce around. You see, just like the perfume. How come you smelled it first and you didn't smell it till later? I'm getting there. And so the rate at which it can burn, a candle, depends on the rate at which what happens? The oxygen has to diffuse around the nitrogen and all that. If you don't diffuse any faster, that's as fast as you can go. I saw a teacher once, and I didn't do this. I could do this, but it just cost the school more money. I could order a tank of pure oxygen gas. And first of all, it's dangerous. But what I could do is burn a candle, and I could do like this, burn a candle, and put pure oxygen gas in it, 100% oxygen. Take a little birthday candle, look at a normal one burning, and look at one with 100% oxygen. What do you think the difference would be? Burn it in your air, burn it in 100% oxygen. Any difference? First of all, the flames would be tremendously brighter, 5 times brighter. The brightest birthday candle you've ever seen. And the candle, this one would last for about 3 minutes, 4. This will last for about 10 seconds. Gone. See, God's pretty smart. Because if he wanted the planet to have an atmosphere of 100% oxygen, he could have. And you would get your oxygen faster, wouldn't you? You would. But we wouldn't have fire departments because you'd never get there in time. Anybody caught on fire? It's gone. It's going to be gone by the time the fire department gets there. So God didn't want fires to be that intense. And as you think about this, you're burning fuel like a candle. You are. And how fast can you burn your fuel? Only at the rate at which diffusion can come in. You run out of oxygen, you stop burning your fuel. All right, let's go over here. What is the other kind of flame you can get? And it's called a premix flame. Now, I at one time, I don't have it now, but I used to have a gas stove. Anybody had a gas stove before? You turn it on, and you used to have to light it. Now they have a little automatic lighter, clicker, And what's different about a gas stove flame than a candle flame? Somebody raise your hand if you said, I know. I've seen a gas flame. We have a gas stove right now. You have a gas stove? What's it look like?
What do you mean?
It's what?
What
What color is it?
It's blue.
It's blue. No yellow? Why not?
Because it's not oxygen. There's not the same oxygen.
That's right. What happens is there's a mixer. the gas comes in, which is a hydrocarbon fuel, the same kind of fuel, and the thing mixes a certain amount of air with it, just the right amount of air to have plenty of any oxygen so you can have really, really good burning. So the rate at which I can burn fuel depends on how fast the fuel comes in now. It didn't depend on diffusion at all. And so Bunsen burners, that kind of thing, those are mixed. My car takes fuel and in a carburetor mixes air with it, so I get pretty good burning there. But what about a campfire? Diffusion fed or pre-mixed? What do you think? Lisa, what do you think? Campfire. Campfire pre-mixed or diffusion fed? What? You got a 50-50 chance. What is it? It is. I don't remember last time in a campfire. Do you remember anything mixing vaporized wood? What? Wood doesn't get vapor. Yes, it does. What? Okay. Wait a minute. So we have two kinds of flames, and I want to show you this new thing here now. We're getting into chemistry quite a bit now. Look at this right here. Burning means combined with oxygen if there is plenty of oxygen. And that's what happens most of the time in a pre-mixed flame. If you have plenty of oxygen, plenty. If there's plenty of oxygen, here's what happens. The hydrocarbon reacts with the oxygen and makes these two things. It makes water and carbon dioxide. You say, wait a minute, where's the water coming from? I'll show you. Give me the hydrogen atoms from the hydrocarbon and combine with the oxygen atoms from oxygen, and you get water. Take the carbon atoms and combine them with oxygen, you get carbon dioxide. Oh, I didn't see that. I didn't see that at all. Well, some of you weren't looking. Now, I will tell you that I'm going to have trouble seeing the carbon dioxide no matter what. If I get down to about 110 degrees, negative 110 degrees Fahrenheit, I'll see carbon dioxide. It's called dry ice. But I didn't have that kind of temperature, so that's why you didn't see the carbon dioxide, did you? But many of you did something like this. Many of you did this. You sat there, you saw it getting foggy. Isn't that what you said? The beaker got foggy, and the flame got smaller, and then it went out. And you said, wow. And some of you are so interested in how long it took. I think that was great. But then you just put the beaker by the side. You missed it. You missed it. What is this? What is this stuff? What is that? And everybody wants to say, oh, condensation. What's condensation? It's water. What? I didn't put any water in there. It came from the chemical reaction, didn't it? So there was water coming through, and it came from the candle. And if you noticed that and you figured that out, that was pretty smart. You're pretty smart if you figured out that water came from the chemical reaction. Now, what happens, though, in a diffusion-fed flame when maybe you don't have enough oxygen? What happens when you don't have enough oxygen? And that's what a candle flame is. It never really gives enough oxygen to burn the fuel. Then it's called not complete combustion, but incomplete combustion. Now watch right here. If you have incomplete combustion, you'll still get some water. You'll still get carbon dioxide. But then you get this nasty stuff, carbon monoxide. That's not good. The good news is the candle only puts out a little bit, and we had airflow. That was good. And then you get this stuff. This is carbon that never did combine with oxygen. And what is that called? What do you call the carbon? Oops, I didn't have my goggles on. Why did I do that? What do you call carbon? Whoa. Oh, look. See my goggles? Wait a minute. Wait a minute. I'm burning fuel. I'm taking in oxygen. I'm giving off water. I'm giving off water. I'm like a candle. Okay, now, so what if I interrupt the flame and say, I caught some of you. I got some right there. I got you. Oh, give me some more. Some more. What's that? What is that? And that's carbon, and that's soot. Okay? And that is carbon. Oh, where'd you get the carbon from? Carbon doesn't look like carbon when it's in this compound, does it? The wax? No. And look at this, carbon. Hey, carbon. See that? Carbon. See? All right. So anyway, you have that. Oops. All right. So now, I will tell you that even in your home, most of you have gas furnaces. Is that correct? Some of you have electric heat, but I bet a lot of you have gas because it's quite a bit cheaper. And anyway, the good news is that most gas furnaces, if they don't break, they're about 99.9% efficient. Means they mix the air perfectly with the fuel and you don't die. But if something over time happens to that little area where it mixes, it could be mixing it wrong and you could get a lot of carbon monoxide and you will die. That's why homes today are required to put in a carbon monoxide detector. You understand that? Most of the time, your furnace works. But if it stops working, something wrong, you need to know it. You need to know that you can be killed by your own furnace. Now, don't go home, you'll be all right. Just ask your parents, hey, do you have a carbon monoxide detector? And if they say yes, hey, you're supposed to change the batteries once a year. Did you do that yet? Ask them about that. Now, my carbon monoxide is so annoying. If that battery is getting close to running out, it just beeps, and then it waits 5 minutes, and it beeps all night. And so I got to go get the battery replaced, okay? So most of them today, they actually are annoying to the point where they don't let the battery run out. Now, don't do this, though. You can take it off the wall, take the battery out completely, but then you're not protected. Does everybody get that? You won't be protected if you do that. All right, so everybody understand two different kinds of flames, right? Okay. Let's go to, this talks about the different zones here. Let's see, here's this zone. Let's see, here's a zone. Here's another dark zone. Okay, now, let's talk about this. It says the highest temperatures are not found near the wick, the top of the wick, and it talks about different temperatures. But where is the, oops, I don't see it. Wait, here it is, down here. What about this area right above the wick? Why does it look dark? Why is there a dark zone? And let's read that real quickly. It says here, the relatively cool region just above the wick is the dark zone, dark cone. There, released molecules of fuel are insufficiently heated and they have so little oxygen that no light is emitted. Now, I did a little experiment one time. Do you remember that? I actually took stuff from the dark zone. So you can take stuff from the dark zone and then push it back in the flame, into the hotter part of the flame. Take it out. Remember this? So what is in the dark zone? Notice how the flame went down when I took the stuff out? Ooh, fuel. I'm taking fuel out. It's not hot enough to combine with oxygen at that point, but it's vaporized, isn't it? So it's vaporized fuel is right in there. So I took it out of there, put it in the hot part of the flame, and it underwent combustion. Does everybody know why the dark zone? And so since almost no burning is taking place there, no light is being emitted. And that's why it's kind of dark. Now, one thing I want to show you, which is, I really had no idea about this until about 30 years ago when I read this. Let's see, where am I at? I'm going to go to the next part. Where's the luminous zone? Oh, here it is. Let's go to the next page. It says here, to me, the most interesting portion of the candle flame is the yellow region, which is called the carbon zone or luminous zone. There, solid carbon particles, called soot, are heated and they incandesce. Now, that's a word that I knew, but I don't know if you've ever heard of it. Have you ever heard the word incandesce? The light bulbs that I used my whole life until lately, they were called incandescent light bulbs. Yes?
The yellow ones, like they give off only the yellow.
Well, I don't know. A 100-watt incandescent bulb looks pretty white to me, but they don't look fluorescent. Look at these fluorescent ones. They look pretty white, don't they? But a 100-watt light bulb, I don't think it looks yellow to me, but I know what you're thinking. You're thinking that, to me, they look yellow to you, right? So here's what I have. The incandescent bulbs, if you could look inside them, and sometimes you can buy clear ones, you'll see a little wire in there. And the electricity runs through that little tiny wire, and it excites the atoms so much that they start glowing. And that's how a light bulb works. That's how Edison light bulb worked. The electricity ran through that wire and excited them so much, heated them up so much that they started glowing. A piece of wood that can be heated up, besides catching on fire, it can also incandesce. A coal can incandesce. And so they're called incandescent light bulbs because they did that. Now, the modern light bulbs are some of them are called, let's see, LED. You have LED? Is that the kind you're buying now? LEDs don't have a little filament in there. They don't have a little thing that glows. Just like these fluorescent tubes, there's no wire that runs down the middle of the fluorescent tube. It's mostly a vacuum, and it has a powder coating on it. And electricity runs from one side of the tube to the other, and it excites the powder in there, and it makes it glow a little bit. Okay, so anyway, so the yellow portion, he thought was very interesting because it was yellow. But why, and this is the question I want to ask before we leave today, why do you even see a flame? Why do you even see a flame? And I will give you a clue. I'm going to give you a clue. What is it that's going on in the zone, in the yellow zone? Now, what I'm going to do is interrupt the yellow zone before they get hot enough. There's something in that flame. If I don't let it get too hot, I can catch them. And there they are. What is that? What is it? Carbon. It's soot, isn't it? Now, I know you don't, I know you haven't, it's hard to believe, but the soot particles are coming up in the fuel, soot particles like this, and they haven't combined with oxygen yet. They have not combined oxygen, but they're getting hot and hotter and hotter. And what do? Starts with I. What do the carbon particles do? They incandesce. The reason you see a flame, the reason you even see the flame is soot. It's soot that has not had a chance to combine with oxygen yet. And that's what's there. If it wasn't for the soot, you wouldn't see it. Now, when the carbon particles get hotter and hotter, they combine with oxygen and make CO2, and you don't see it. Sometimes, some of you did this. Some of you would shake your candle. And if you did it just right, sometimes you get a little black smoke. Did you ever get black smoke? I'm trying to think how I do this. What was the best way to get black smoke? I'm not getting it right now. Come on, candle. Come on. Anyway, if you do it, if you wiggle quite a bit, you'll get some black smoke. Well, that's some soot that didn't get hot enough, and it gets given off as black smoke. I'm gonna show one more demonstration, and that'll be it for today. I might be able to make this work, and I might not. So we're gonna try it. I'm gonna turn the lights off, and hope that it works well. I would like to show you. Oh, my blue screen there. It sometimes works and sometimes not. Now, what this guy did and what Faraday did is they had sunlight, and they bounced the sunlight in with some mirrors, and they put a bright light at the flame. You say, well, that's kind of dumb. Who wants to shine a bright light at a candle flame? Well, a scientist would. So watch up here. First of all, we're seeing something happen. Can you see in the dark zone? The dark zone is making a shadow. Now, what is it that makes a shadow? It's things that block the light, isn't it? And I'm getting a little bit. Can you see the image a little bit? If I get the right focus, I don't know about that or not. How about that one? But anyway, there's carbon particles in there that are blocking the light, and it'll make a shadow. It didn't make a very good one there. But that's what's in there. That yellow zone has a lot of carbon particles in it. Like that. Okay.